So you'll notice on your formula sheet, which you'll be given on the day of the test, any quizzes, AP exam, this section on gases, liquids, and solutions has a lot of formulas, but most of it you're already familiar with, like PV equals nRT. That's your ideal gas law. PA, partial pressure of gas A, is equal to the total pressure times XA. And remember, where XA we've already talked about as your mole fraction. And we talked about gaseous mixtures. The total pressure is going to equal the sum of all the partial pressures of the gases in the mixture. The rest of these you have seen before, N being moles. And the way we calculate moles, if we have the mass of a substance, we take the mass and we divide by the molar mass. One thing I want to note about this equation here, this is something that we do like second nature in our class. Just watch out though for the way you're writing these symbols. That lowercase m, that is mass, and the uppercase m represents molar mass. If it's helpful for you, you can replace that capital M with two capital M's. So you can think of it as molar mass if you would like. That will become helpful, especially when we start to talk about something called molarity a little bit later. And then here we have Kelvin is equal to degrees Celsius plus 273, and then density is equal to mass divided by volume. And we have also seen kinetic energy is equal to 1/2 the mass times velocity squared. Now, just in case you forget what any of these symbols represent, on the right-hand side is what each one of those means. Don't worry about this section here, where it starts talking about molarity. That is for our next unit on solutions. Okay, so where I drew this purple line, that is where your gas is. That's where we stop. Notice over here on the right hand side, your gas constant R is given to you in different units. The one that you are most familiar with is the 0.08206. The unit is liters times atmospheres divided by moles times Kelvin. When you see that -1 as your exponent, we know that those variables are going to be in the denominator. Now, there are different values for R, but I just recommend sticking with 0.08206 because those are the units that we're typically going to work with. So if you stick with liters, atmospheres, moles, and Kelvin, you're going to need to use the 0.08206. These other R values are used when you have different units for your pressures, and even for this one here, joules, where you're not going to look at that anytime soon. Note here that 1 atm is equal to 760 millimeters of mercury, and 760's torr is given to you, as well as STP is equal to 273.15 Kelvin and 1 atm, and an ideal gas at STP has a volume of 22.4 liters for every 1 mole. We will talk about this in this video lesson. A lot of times we're asked about the density of a gas or the molar mass of a gas, and we're asked to calculate those things. And oftentimes they don't tell us the identity of the gas, so we can't just go look it up. We have to use the measurements given to us in the scenario. So we know that density is equal to mass over volume, but a lot of times we're not given the mass of the particular gas in our sample. But what we do know is the ideal gas law, PIV-NERT, and we're able to derive a density equation and a molar mass equation just from the formulas provided here. So I'm going to show you a series of steps that we use to derive a density equation for gases and then a molar mass equation for a gas. Okay, so it has to do with using these 3 equations. Okay, so I just wrote down the three equations that are provided to me on the formula sheet, and I'm going to show you how we derive the equation for density of an unknown gas. But if we know certain things about like its pressure and its volume, we can calculate its density. So first thing I noticed in our ideal gas law, also called PIV-NERT, is that we have this variable of n, okay, which is your moles. And we also have an equation of n over here, which we know is the mass divided by the molar mass. So I'm going to substitute in mass divided by molar mass in for n into our equation. Okay, so all I've done is replace the symbol n with mass over molar mass. I'm going to rearrange this. I'm going to clear out the denominator. So we're going to go molar mass is equal to P times V. I'm sorry, molar mass times P times V is equal to RT. And then we're going to rearrange this to, whoopsies, sorry, that is equal to mass times RT. Now I can rearrange this and make it look something like the density equation. So density is equal to mass divided by volume. So that's exactly what I want to do here. I want to rearrange these variables until I have mass over volume. So I'm going to divide both sides by RT. And so I have molar mass times pressure times volume over RT is equal to mass. And one last thing to make this look like the density equation, I need to divide both sides by volume. And when I do that, we get molar mass times pressure over RT is equal to mass over volume. Voila! Here is our density equation. M over V, mass divided by volume, is density. So in other words, density is equal to the molar mass times the pressure of the gas, all divided by RT. So I'm going to clean this up a bit. So density of a gas is equal to the molar mass times the partial pressure, all divided by RT. That's pretty helpful to know. Another thing that we're often asked is to calculate the molar mass of the unknown gas, and a lot of times they'll give us the density and the partial pressure and the temperature. So since I already have this density equation, let's just take it one more step. Let's rearrange it and now solve for that molar mass piece. So if I rearrange this, we're going to get cross multiply d times r times t is equal to molar mass times the pressure. And so if I solve for molar mass is going to be equal to dRT over P. That's also another very helpful equation to know. Again, it's not on your equation sheet, but it is going to come in handy. It's going to allow you to do some of these calculations a whole lot faster if we just know this equation. And this one as well. But I walked you through the process of how you could derive it. In case you don't remember these, you can always use the ideal gas law equation, the mole equation, and your density equation to solve for the density of the gas and the molar mass of the gas. So I would know these, memorize that one. A little NIMSY trick that I've learned over the years. It's kind of silly, but it might help you. So we've learned this little mnemonic device to help you remember that molar mass is equal to dirt over P. They often say kitty cat, molar mass kitty cat is equal to dirt over P. Dirt really being DRT. And think of a kitty cat going to the restroom in their litter box, and a good kitty cat is going to scoot some dirt over their pee in their litter box. So molar mass, kitty cat, dirt over pee. I told you it was silly, but it might help you. All right, on to some problems. Okay, number 1. Go ahead and hit pause, give you time to record the question, and we'll come back and solve this problem. Okay, I have gone and identified what all of the numbers represent. We have a molar mass of 32 grams per mole. Remember, that is always going to be the unit on molar mass. Molar mass is how many grams for every 1 mole of a substance. We have the pressure given to us, they give me the temperature, and they're asking me to solve for the density. So what was that little saying? And actually, you really only need to remember this one, and then you can derive the density from there. Molar mass, kitty cat, dirt over pee. Told you it was silly, but I think it helps us sometimes remember. So we're just going to rearrange this, solve for D, our density. So density is equal to molar mass times the partial pressure over RT. So now it becomes a plug and chug into the density equation. Okay, I've substituted in my values with my units. One thing to watch out for, because we're using the R value of 0.08206 liters times atmospheres moles over Kelvin, we gotta make sure our pressure is giving us in atmospheres, which it is. One thing about temperature for gas law problems always is in Kelvin. No matter what equation that we're using, we are using Kelvin. So note here, I did change my temperature to Kelvin by adding 273 to our degrees Celsius. Okay, so we plug this into the calculator and we're going to get an answer. I get an answer of 1.95 grams per liter as the density of this gas. Please note your units here. We are solving for density, which is mass divided by volume. So that's why we have grams divided by liters. Let's try another problem. Question 2. We are given moles of an unknown gas, and it's in a container, and we know the density, but now this time they want me to calculate the molecular weight. So please hit pause, record the question, and come back. All right, this question has density in it, so probably an equation comes to your head. Molar mass kitty cat equals dirt over P, but problem is wrong. There's no pressure given to me. How are we going to solve for molar mass, which is another word for molecular weight? I know that's molar mass because look here. They want grams per mole. That's molar mass. So we got to use the information given to me. It looks harder than what it actually is. We know that the density is 4.15 grams per liter. I'm going to use that as my starting point. Grams, and I'm going to rewrite it as 4.15 grams over 1 liter. And I know I need to turn this into an answer in grams per mole, because I want the molecular weight. No, this is going to be my answer here. So I somehow have to convert these grams per liters into grams per mole with the information given between the problem. You do know something. You know that the volume of the flask is 3 liters, and that inside of those 3 liters is 0.205 moles of this gas. So we know 3 liters is equal to 0.205 moles of this gas. So we can kind of use that in our dimensional analysis here. And we're going to use the power of canceling out units to help us put particular units in certain locations here. So since I need liters to cancel out, and my starting point has liters in the bottom, I'm going to take those 3 liters and put it on top so that those liters cancel out. Well, what is that equal to? 3 liters, what did we say? 3 liters was equal to, 0.205 moles because they're in the same container. 3 liters contains a 0.205 moles. Alrighty, so moles don't need to cancel out. They need to stay in the denominator because that's where I have it in the answer. And then I have grams in the numerator still, and that's exactly where I want the grams in my answer. So this looks good, guys. So now we're just going to do the math here. 4.15 times 3 divided by 0.205. We get an answer of 60.7 grams per mole. This is the molecular weight, i.e. molar mass of our unknown gas.